Thank you for inviting me here. It's wonderful to be back in Iceland. Let's see now. Chris? I have a mountain here to look at. So this is an overview of the talk, 25 minutes presentation, and then 10-minute discussion with an introduction and modeling human thinking, then modeling arbitrary domains, and modeling human thinking in arbitrary domains, and finally a conclusion. Yeah, so this is a so-called one-trick pony. The only thing it can do is to carry a goat on its back. And we have a lot of one-trick ponies also in technology. So here's an example. This is a wrench that can do one thing, and a pocket calculator which can only do arithmetic. And then we have collections of one-trick ponies, you can say, single-domain tools. For example, this Swiss Army knife can do many things. It's just a collection of single-domain tools. And the same holds for an iPad, for example, with lots of different applications that are specialized in basically one thing. But then we have multi-domain tools in the brains of mammals, for example. They can adapt to many different situations and they can learn new things. And if we look at AI today, we have a lot of amazing programs, but they are all single domain. Programs and robots. For example, we have robots that can work in car factories or mow the lawn. But those are fairly static and predictable domains, the same all the time. For example, in industrial environments. But out in the wild, things are much more difficult. So we don't have any multi-domain robots that can, for example, work as butlers in arbitrary homes. And we don't have construction workers that can go to any construction site and then work as construction workers there. And that would require a system which could function in more dynamic environments. And that we don't have today. So we have the same strategy that Chris was mentioning in the introduction. We look at who can do this, who has this versatility in the animal kingdom, and we see animals and we see humans in particular. So our idea, and many other people's idea, is to try to mimic the way a human develops a child and see where that can bring us. So now let me introduce Alice, who is an imaginary schooled girl with multi-domain capacity, like most humans. And she has a number of properties that we will assign to her because she's just imagined. So, for example, she learns from examples, experience. And here's a quote by one of the founding fathers of constructivism. He says that the thinking subject has no alternative but to construct what he or she knows on the basis of his or her own experience. So everything is constructed, all knowledge is constructed. Also mathematical knowledge, for example, according to him. And Alice, she also prefers simple explanations. So, supported by this quote, for example, the grand aim of all science, and I think it also holds for everyday reasoning, is to cover the greatest possible number of empirical facts by logical deductions from the smallest possible number of hypotheses or axioms. Okay. And then Alice, she forms her own hypotheses also. So here are two stories about Alice. So the first one is that she had learned that 0 times 0 is 0 and 1 times 1 is 1. So there's a pattern there, right? Based on those examples, she formed the general hypothesis, maybe x times x equals x. But the next day she found out that 2 times 2 is 4. Perhaps someone told her. And then she concluded that no, 2 times 2 isn't 2. So there we have a counterexample. And then I should abandon my general hypothesis. And in the second story, she has learned that 2 times 0 is 0 and 3 times 0 is 0. And again she sees a pattern. This time she sees the pattern x times 0 is 0 for any x. But in this case, she never discovered any counterexamples. It happens to be a true statement. So that's why, probably. So since she never discovered any counterexamples, she kept it and she never abandoned it. Okay, and then we are also assuming that she makes her own computations. So we think that when Alice constructs a calculation in arithmetic or a sentence in grammar, she basically does the same thing. She makes computations using the hypotheses that she has learned from experience. So she combines those hypotheses into a computation. Yes, and then she has something in common with all of us, I think. She has bounded cognitive resources. Cognitive resources such as working memory, long-term memory, and span of attention. So she's like most of us, I think, is Alice. And those are the assumptions about Alice. And now let's see how we can try to formalize that so that we can build a program eventually that will mimic Alice. So now we turn to a more formal part of the presentation. And so we work with a finite set of symbols that we write in the typewriter font. And we have 3 symbols that are special that we call variables, x, y, and z. And then we can form a finite sequence of symbols. For example, 2 plus 3 is such a sequence, x times y, and Alice runs. It's all about symbols, right? And then we introduce equalities and inequalities based on those strings. So we can have one string and then a sign in the middle and then another string. And the sign in the middle can be either equals or doesn't equal. So there are some examples. 2 times 2 equals 4. X times 0 equals 0. Alice runs equals okay. That's an okay English sentence. But they runs, that's not an okay English sentence. So these are just examples of some equalities and some inequalities. There's no claim yet about the truth or falsity of these statements. Okay, and then when we have equalities, we can form theories. And a theory here is simply a set of equalities. So example 6 there could be a very simple example of an arithmetic theory. So 2 times 2 is 4, x times 0 is 0, and x plus y equals y plus x. Then if you know that, you know a little bit about arithmetic, not too much. And grammar, this is a very small grammar with some equations. So Alice runs is okay. Alice can always be replaced by Stella while preserving grammatical correctness. It's the meaning of the second equality. And then similarly, runs can be replaced by plays while preserving grammatical correctness. Changing semantics, of course, but preserving grammatical correctness. Okay, so those are examples of theories. And why do we introduce theories? Why do I introduce theories here? Because I want to introduce computations. We said that Alice uses computations, so we have to model that somehow. And she does that by using a sequence of strings. And those strings, one is obtained from the other by applying some axiom in the set. So I'll show you a few examples so that it will be clear. So here's a computation in arithmetic, and the theory that Alice uses in this case consists of the 3 axioms written to the right. So you see in the first step, for example, she will replace 2 plus 4 by 6. And then in the second step, she replaces 6 plus 1 by 7. And then 6 times 7 equals 42. So in this case, she uses her math knowledge, her multiplication and addition tables that she learned at school, perhaps, to compute this term on top. And here's an example that involves variables. So she computes that 0 times 12 equals 0 in this case. And she can do that because she can first switch according to one of her rules and move over to 12 times 0 instead. And then she knows that anything times 0 is 0. So that's how she can compute that particular term or expression. And then here's a language example. So now we are assuming that she has the knowledge, the language knowledge written to the right, the one we saw before also. And from there she can conclude that a sentence that she never heard before, perhaps, is grammatically correct. Stella plays. Someone says Stella plays. And then she knows that, well, I can always replace plays by crawls. I know that's always all right. And I also know that I can always replace Stella by Alice. So I'm going to preserve grammatical correctness. And then I get Alice crawls. But I know that Alice crawls is actually a correct sentence. So then I conclude that Stella plays is also a correct sentence. Okay. And we also said that she had bounded cognitive resources. So our model should have that as well. And we do that by using the ordinary computations, but limiting the length of the computations. Like her span of attention, for example. She can't think infinitely deep thoughts, so to speak. She can think, in our case, 20 steps, which is not bad already. And she also can't keep any amount of information in her working memory. We can only store like a telephone number there, roughly, a short one. So that's why in our bounded computations, the width is also limited. So the terms that appear, or the strings that appear in the computations can't be too big. So we put them somewhat arbitrarily. We say that the max length of the computation is 20 steps, and the max width of the computation is 8 symbols. With some support from cognitive psychology. Okay, and then we introduced this, notation. S turnstile T S prime means that there is a bounded computation in T, starting with S and ending with S prime. So then we can use some axioms, and then we can start making computations using those axioms with our bounded resources. And the good thing about this, about moving to bounded resources, is this observation there. If T is a finite theory, then there is a method for checking whether S prime follows from S, whether there is a derivation starting at S and ending at S prime. And that doesn't hold in general if we are looking at unbounded computations. So this is a big benefit that we get for free. Okay, so that ends our formal model of Alice and the way she makes computations. But Alice, she lives in some environment, in some domain that may be partly unknown to her. So we have to model that domain as well. And we say simply that a domain is a set of variable-free equalities and inequalities. So the domain describes the environment, which things are true and which things are false in the environment. So for example, in an arithmetic domain, we could have those 3 equalities and inequalities 2 plus 3 equals 5 is true in that domain. 2 plus 3 equals 1 plus 4. 1 plus 1 is not equal to 3. So that domain looks very much like our own familiar arithmetic domain. And in grammar, happens to be English in this case, Alice runs, that's okay. Runs equals plays, that's also okay in that domain. And but Alice does not equal runs. You can come up with a sentence which contains Alice and is correct, but you are not able to replace Alice by plays and keep the correctness of the sentence, preserve it. Okay, so a domain can be anything like that. So it doesn't have anything to do with arithmetic or grammar, but these are just examples. Okay, and now we have this program called Alice. We want to model human thinking the way we did it before in an arbitrary domain. So a human who lives in a certain domain will gradually develop a theory about that domain. And this is how our program, this is what our program Alice does, and this is how it works. So Alice is a developing agent, means that Alice has a set of beliefs which develop with time. Sometimes some parts of the theory will be removed, thrown out of the belief sets, and some other beliefs will be added. So it's a dynamic thing, something that learns just like a baby, for example. Okay, so Alice is a developing agent living in a certain domain, which is unknown to her. Alice stores her beliefs at time n in a theory Tn. And she starts with an empty theory. We're assuming that she starts with, it's like a tabula rasa, nothing. And also, like we said before, the size should be limited because she also has a limited long-term memory capacity. Okay, so that's the rough picture of the program. And now what happens at each repetition, at each time step, is this. First, Alice receives a question from the environment, or a challenge from the environment. And it concerns S and S prime, the relation between them. Do you think that they are the same? The environment asks. And then Alice will try to compute an answer, and then get a feedback from the environment, depending on if she's right or wrong. But how does she compute? What does she do? Well, she checks whether S follows from her present set of beliefs. S prime follows from her present set of beliefs from S. And then she answers yes or no, depending on how that goes. And then she will get the reward or the punishment from the environment. So this means that the more she has adapted, the more she has understood of the environment, the more she will get rewarded. And if she hasn't understood the mechanics behind the domain, then she will get punished all the time instead. So there will be a measure there. How well does she understand her environment? How well adapted is she to her environment? Okay, and then the last step. Alice will learn from this experience. So either throw out some beliefs or add some new beliefs, or maybe keep it as it is because it just earns her a lot of reward. So in this way, Alice represents a dynamic agent which will gradually develop a sequence of theories, hopefully better and better adapted to the environment. Okay, and now the demo will actually be of this form because of some technical issues that we had experienced yesterday. But these are screen dumps from the program. And up in the left corner, you see the challenges from the environment. So for example, the first challenge there says that, do you think that 2 times 4 is 8? Okay, if you do, then you will get, in that case, 1 point reward. And the second, do you think that 2 plus 1 is 3? Yes, if you do, then you get rewarded. And then there's a negative one there. Do you think that 1 plus 0 equals 10? Oh, if you answer yes to that one, then you get punished instead. You get -1. Okay? So Alice gets to see random parts of the environment. And then she gradually develops this theory of the environment. So, for example, she knows there that x plus y equals y plus x. She also knows that 0 times x equals 0, and a few more ones. You see the ordinary algebraic axioms will develop in this way. And we can also give her we can give her any domain. And we can take English, for example. We could have taken Icelandic also. So she gets some examples of things that are correct and incorrect in English. And she will develop a theory like this. For example, yes, I think I can always replace Bob by George. And I can replace Paul by he, Alice by she. I think that, John plays is an okay sentence, and so on. Okay, so that's just an indication of how it works, the program. And then, finally, this is a little conclusion. So this program, Alice, can develop complete theories that are able to prove all true things about the environment, in the case when the environment is arithmetic, for example, and also some propositional logic and other domains. And it also reaches human level quickly from these examples in the cases that we looked into, logic and arithmetic. And so in summary, Alice can learn at least 2 domains. We're looking for something which is domain independent. And now we are investigating if there are other domains that Alice can learn as well. But we are pretty hopeful because there's nothing about grammar or logic or mathematics built into Alice. So she's a general agent operating in the same fashion with all those domains. So thank you. That's the first part. And
so now we have time for some questions. Maybe you can repeat the questions.
yes, is it possible that we go into an infinite loop?
Yes.
Somehow? Not really, because we are working with bounded cognitive resources, and there are only finitely many things that follow there are only finitely many things are computable. So I don't think so.
So one conclusion could not lead to a set of actions that will be recomputed elsewhere, and then.
Okay. In that sense, it can. It could happen. Yes. Yes. Some more questions. Easy ones.
Yeah, no, I was just wondering if you thought to maybe be applied with like human learning, like with the positive and negative towards
Yeah, I mean, we are making some assumptions in the constructivist tradition, and then if we can show that those assumptions are enough for learning certain things in a certain way, then it can have a little bit of feedback on those theories, perhaps. So I think that this is vaguely relevant, at least, to pedagogical research.
Yeah.
Is there something inherently similar to the domains that you've picked so far? Or do you think there are domains out there that will have features that are not going to be captured at all?
Yes.
Repeat the question.
Yes. So Hannes is asking if there are other domains out there that won't be captured by this approach, and I would guess so, definitely. But I think that quite a few domains involve symbolic manipulation. For example, many board games. So I have and many of the traditional AI problems, for example, they're also purely symbolic in nature. So I have pretty good hopes about those, but I also think that there are lots of other things that are not covered by this model.
I have a follow-up question on that. So what is the main difference in what you know of the general game playing approaches that have been tried so far and Alice? Are there any differences that you'd like to highlight?
Well, I mean, if you think about deep learning, for example, which have been used successfully in programs that play many games that you talked about in the introduction. And yes, I think that the two approaches are very different, because this is not a network-based model. This is I don't know, a kind of traditional model where you have a theory and everything is just like axioms. It's a logically inspired model, the one we have.
There's a question here.
It seems to me that the interesting thing about a system like Alice that would stop it just being a fact collector is the point at which it starts to compress facts
Yes.
that are given into general inferences.
Exactly.
So how does that work, and what's the threshold for that? Because you can be told that 2 times 3 equals 3 times
Yeah.
2, and 3 times 2
Yeah.
equals 4 times 3, but what point do you say, I think A times B equals B times A, always?
That's a very good question. Make sure you repeat the question so that everyone...
Okay, can I do that? Well, yes. How do we compress the data? And because then that's where the intelligent part starts. I think you're saying, right? And then I would answer that we compress the data when we start making computations based on those data. So we draw the consequences from the data. So that's one way of compressing. And another way of compressing, which we actually haven't implemented really in this particular system, is to look for, well, yes, I'm sorry, yes, we do, we have implemented that. It's a mechanism which prefers powerful axioms to weak axioms. So it will automatically prefer general axioms to specific axioms. An example is 2 times 0 equals 0. Well, it's a good and correct axiom, but it's not at all as good as x times 0 equals 0.
What role does you construct on logic, but what about fuzzy logic or random variables, and also variables that are not discrete, continuous variables?
Yes.
How does that?
Yeah, the thing is that first order logic, for example, is about symbols also. And first order logic is not decidable, as the technical term goes. So there's no way of computing it, knowing what follows from what in general. But when we restrict attention to bounded cognitive resources, then all of a sudden it becomes decidable, so that it is possible for us to determine whether something follows using first order logic from something else with those bounded computations or proofs.
Yeah, one more here. Yeah, I wonder about the rewards and punishment.
Yes.
Is the information, it looked like, you know, the information about how many points Alice gets for solving each thing is already
Yes.
included in the task?
Yes, I mean...
Is she taught to value
Yes.
benefits and rewards?
Yes. So where do we get our rewards and punishments from, basically? And yeah, it's that we can imagine that they come from any external source. So we can also weigh the different the different questions. So this question is very important. So then you get 2 points if you answer it correctly, but you get -2 points if you answer it incorrectly, for example. But the actual punishment and rewards, they are specified from some external source, and this is inspired by reinforcement learning, where they have a similar setup.
So she collects points.
Yeah, Alice will collect points. I mean, her goal is to, she's greedy, she's hedonistic, she wants as much reward as possible. That's her.
I hope you're quick.
Another human part of Alice, actually.
So last question here.
Yes.
I'm not sure I got it if you explained it, but how do you generate the training questions?
Yes, we can. We in this case we just we look at arithmetic and grammar, and we generate those by a grammar generator, which will generate samples for us, and by using random expressions in arithmetic, evaluating them, and then feeding them with also random positive or negative.
Isn't there a lot? I mean, if you want to learn something, a big part of training is question generation?
Yes, but I mean, it will adapt to any kind of environment with, I mean, good or bad question generations. So yeah, I think that's that's the way it should be. But yeah.
Probably just learn slower if it has
Yes,
more
exactly.
noise.
It will learn slower, and that's also another pedagogical feature. If you present the same material in a different order, that may affect the learning. Yeah, so it's like this. If you read a math book in the wrong order, starting in the back, then you will learn less well than if you read it forward. So the order in which the examples are presented matters for the learning outcome.